The students might find the way, or the previous way, of carrying out the cross product of the vectors a and b a bit tedious and difficult. So here in this session we're going to use the determinant of a matrix as an alternative way in order to obtain the third vector. Well, the cross product here can be written in determinant form. The determinant here is written between these, is represented by these two sidebars, where the first row is the unit vectors I hat, j hat, and k hat. And we're going to write the second row by starting with the first vector. The second row has three components, can be written as second row. And finally, the third row is going to be the components of the vector b. So to evaluate the determinant, we're going to start with I hat, which is located in the first row and first column. So writing down I hat and then looking for the cofactor of I hat. To do that, we cross off the first column and the first row, and then finding out the cofactor of the remainder of the determinant. This cofactor is simply the product of ay and bz, and then minus the product of az by. And here we are. This is the first component of the third vector. This is the x component. And then for the y component, we're going to start with j hat and writing down j hat, but this j hat must be preceded by a negative sign instead of positive for the first one. And then crossing off the column and vector belongs to j hat, and then determining the cofactor of the remainder of the determinant by taking the product ax bz minus the product az bx, and here we are. This is the y component of the third vector. And finally, for the z component, we're going to take k hat, and then k hat must be preceded by a positive sign, and then crossing off the column and the row that corresponds to k hat, and getting the cofactor by having the product ax by minus ay bx, and here is the third component of the vector. In this example, we'll find the cross product of the two vectors a and b, where a with 4 units and with an angle of 53 degrees with respect to the positive x-axis in the counterclockwise direction, and b with a magnitude of 5 units and with an angle of 130 degrees with respect to the positive x-axis in the counterclockwise direction. Here we're going to find the cross product in two ways. The first way is by applying the cross product relation a cross b equals the product of the magnitudes of a and b times sine theta, and that's multiplied by unit vector n hat, which is perpendicular to both vectors. The right hand side of this relation will be applied in this way of finding the cross product. So to do that, the magnitudes of a and b are given. However, the angle between the two vectors is required to be obtained, and that is 77 degrees by subtracting 130 minus 53. And then the magnitude of the vector product is simply the product of the magnitudes when substituted into the relation times sine 77, and that is 19.48 units square, and that represents, as we said before, the area of the parallelogram spanned by the two vectors A and B. The direction of the cross product can be obtained by using the right-hand rule, and this is obviously going to be perpendicular to the plane and the positive z-axis. So the result is going to be 19.48 k-hat unit square. We're going to solve the same problem by following a different way for the cross product. So this will be conducted by using the left-hand side of the cross product relation and evaluating the determinant of the matrix for the cross product A cross B. This requires obtaining the three components for each vectors, because as we said before, the vector product is defined in three-dimension space. So the components of the vector A can be obtained directly by using the magnitude of A and its corresponding angle 53, and that's going to be 2.4. And the Y component is 3.195. However, the Z component is 0, obviously, because the two vectors are defined in XY plane. Regarding the second vector, the X component is obtained to be minus 3.14 units. The Y component is 3.83 units, while the Z component is 0. This is the first step towards obtaining the result. The second step is writing the vectors in terms of their unit vector rotations, and then substituting the values of the obtained components for each vector, and then write down the determinant of the matrix by substituting all the components obtained in the early stage. Doing that, we'll have 2.47 for AX, 3.19 for AY, and 0 for AZ. And for the components of B, we have minus 3.214 BX, and for BY 3.83 and 0 for BZ. And evaluating the determinant, obviously here we will get just one row by just crossing off the K component. We'll get just the Z component here, because the other components is going to be 0 as long as the last column have two zeros in it. So, and here the final result for a cross product is the same as that obtained before.